Is it easier? It's different. All right. Chapter 13. What we're doing with chapter 12 is we're going to overlay it into the entire term. So we're going to do synthesis most Thursdays. So I'm not going to have a dedicated unit on chapter 12. I found in the past that I could present synthesis as a lecture topic, but it doesn't really stick unless you have synthesis problems to work on in small groups. So we're going to divvy it up into various Thursday activities. But we can now move on to alcohol chemistry. Alcohol chemistry is not too bad. There's only a handful of new reactions, but there are a couple of things that I want you to review at home. I want you to review naming or nomenclature at home. There are two different ways you can do that. You've got section 13.1 in your textbook, or you've got this Khan Academy link. We've covered naming a fair amount already in this course. What do you guys think the first step is? Identify the longest chain, right? So it uses all the same rules that we've already seen with naming, but I would encourage you to go back and practice it because alcohols do take priority now, and so you do have to consider the position of the alcohol. All right, but let's do a little bit of review regarding alcohol acidity. Oh. This would be a good question on an exam. What's the pKa of an alcohol? Something like water. I heard it somewhere over here. 15 point. Oh man, bonus points. 15.7. pKa of alcohols are about 15.7. For a generic alcohol, right around 15. Water is 15.7 exactly. It's a good number to kind of keep locked into your brain because that lets you know whether or not something's more acidic than water, less acidic than water. All right, so if we have water and water, we could have an equilibrium reaction. You guys saw this a lot in Gen Chem, where you can form hydroxide in solution and hydronium in solution. The pKa of hydronium is negative 1.7. Which way is this equilibrium going to lie? Yeah, towards the water side. So if we want to really draw this using equilibrium arrows, we could have it like that. You guys talked about this a lot in Gen Chem. And what was the equilibrium constant for this? It was 10 to the negative 14, right? So the equilibrium really favors the water side. Alcohols are similar, where if we use a functionalized alcohol instead of water, and we have it react with water, the equilibrium's still going to favor the starting material side. What's that? Oh, shoot. Thank you. Good catch. There we go. It should be very little on the product side. Thank you. And we end up with this deprotonated alcohol, and we end up with a hydronium ion. Whoops. Up here we call this hydroxide. What do you think we call a deprotonated alcohol? Yeah, an alkoxide. It doesn't really roll off the tongue, but it's the nomenclature. So hydroxides, the conjugate base of water. Alkoxides are the conjugate base of alcohols. Alcohols might differ a little bit from the pKa of water. You might have a pKa range of all the way from 9 to maybe all the way up to 18-ish. So it can be more acidic than water, or it can be less acidic than water. What do you think could impact the acidity of an alcohol? Going back to first term. Yeah, so sterics could play a small role. Typically, sterics don't play a huge role in acidity, but they can play a small role. So if that R group's super bulky versus like a methyl group, that could change the acidity. What's something else? Resonance, right? When in doubt, resonance. So if that R group has resonance, that could dramatically change the acidity. What's another thing that could change the acidity of an alcohol?
The R group?
What on the R group? So this already has hydrogen bonding, but there was another big feature in acidity. We talked about the atom, its size, and then we talked about resonance. Induction. So if that R group is inductively withdrawing, that can also change the acidity of alcohols. So let's take a look at an example. We've got this plus water. And I'm just going to use regular equilibrium arrows this time. What will your conjugate base be? Not everybody all at once. All right, let's draw it out. Since you guys might have forgotten, our base could grab this proton, dump the lone pair over here. Now we've got an oxygen with 3 lone pairs, which gives it what charge? Negative. And we formed our hydronium ion. This is called a phenoxide. And this is called phenol. It's a special type of alcohol. All right, the pKa of a phenol is right around 10. Why is it so much lower than the pKa of a normal alcohol? Resonance. So in this case, it's important to go back to the topics we covered first term, and we could say that the conjugate base is stabilized via resonance. Which makes this more acidic. There are actually a handful of phenol derivatives where they use both resonance and inductive withdrawing features, and you can get some relatively acidic alcohols by adding on these stabilizing features onto your conjugate base. All right, so water is a pretty crummy base. That means we have to use some better bases if we do want to deprotonate our alcohols. What are some bases that we can maybe use to deprotonate an alcohol? Does anybody have some ideas?
More alcohol.
NaH? More alcohol. Nope. So let's make a list of common bases used to form alkoxides. I heard sodium hydride in the back. That's one you can definitely use. Why do we like using sodium hydride? It's not nucleophilic. What's the byproduct of using sodium hydride? Hydrogen gas. So if we draw this reaction, we can say, all right, this hydride can grab a proton, form our alkoxide. Whoops. So we get oxygen with the negative charge. The sodium's the countercation. And hydrogen gas just bubbles out of solution. We don't really have to deal with it at all. It's pretty handy. There's also another way of forming alkoxides that's more popular than using sodium hydride. However, it's a little bit more dangerous. You can use lithium, sodium, potassium, rubidium, or if you're really, really gutsy, you could use cesium. What happens if you add potassium into water? It explodes. Exactly. What do you think's exploding? Look at the top reaction. What are we creating that's quite flammable? Hydrogen gas. So if you use lithium, potassium, or sodium, you do a similar reaction. In this example, I'll just use potassium, where you generate your alkoxide plus hydrogen gas. However, it can explode. Oftentimes when chemists are doing this, they have to be extra careful. And oftentimes they'll use sodium over potassium because it's a little less reactive. However, people occasionally use potassium too. They also, when they do this reaction, deny it of oxygen. So if you do flood this with an inert gas like nitrogen, you can prevent that buildup of hydrogen and prevent an explosion from happening. So quite often you use inert gas with these.
So K is with H. Is K of nature or just elemental?
Oh, that's a good question. So what does this little circle mean at the top?
Elemental.
It means it's elemental. So in this case, it's just metallic potassium.
So where did the H, another H come from?
You actually get it from two different alcohols. Yeah. So this isn't a true balanced reaction. Let's actually balance it right now. You can either put a 2 coefficient in front of your alcohol or say you create half an equivalent of hydrogen for every one alcohol. Does that make sense? Okay. Yep.
What's causing the hydrogen to leave
Out of solution.
the reaction itself?
So in the reaction, the hydrogen forms a gas. It'll just bubble out of solution. And if you're flooding it with nitrogen, it'll push it out with that nitrogen gas, and you'll prevent hydrogen buildup.
But what in the metal makes the hydrogen?
It gets into oxidation-reduction chemistry. So these will do a really quick reduction. And we're not really going to get into the mechanistic details behind this. The main thing to remember is by doing this, you can form an alkoxide anion, and these are really valuable for synthesis. If we look at this, what do you think we could do with the alkoxide anion? We could form ethers. So in this case, this is a good nucleophile. So it could attack an electrophile and form a new carbon-carbon bond via an SN2 reaction. We saw that last term. It also is what else? If it's a good nucleophile and it's really unstable, it's probably also good at stealing protons, right? So it's also a good base. So we saw these used for E2 eliminations where we could use sodium ethoxide or potassium terbutoxide. Now we actually know how to make that reagent. So for example, let's say I'm running a reaction and I need to form potassium terbutoxide. What starting material and reagents would I need for this? Terbutoxinol? Terbutanol. So we could react terbutanol with what? Potassium metal. So oftentimes what you physically do is you get a beaker or a round bottom flask full of terbutanol. You cut sodium very carefully with something that's the equivalent of a butter knife. It's a very soft metal. You huck a chunk of potassium into your flask, make sure it doesn't explode, and then you can transfer off the slurry that you've made into your flask and use that for a nucleophilic SN2 reaction, or you can use it for an E2 elimination. So we can make these pretty easily. Oftentimes chemists prefer to make these fresh rather than buying them from Sigma Aldrich or another chemical vendor because it's pretty easy to make, and you know the exact way it was prepared and that it's fresh and it hasn't gone bad or anything.
I feel like you downplay the whole not letting it explode.
Yeah, it takes a while. I'm not going to lie. Working with potassium my first time, I was very nervous. My hands were shaking really bad and I didn't enjoy it. But once you get good at it and you get comfortable using inert gases in particular, it's a relatively safe thing to do. Yeah. All right, let's go to a little bit of review. We've got a few minutes left. We've already covered a few different ways to prepare alcohols. So I'll quiz you guys a little. We covered this last term, but I want you guys to help me predict the reaction mechanism. So I've got sodium hydroxide. We could do an SN2 substitute. Oh, shoot, I said it. What sort of substitution is this? SN2. Why is it SN2? Oops. So we've got a good nucleophile. That's a good indication that it's SN2. What about our electrophile? It's primary. And in this case, we've got a decent leaving group. So we can do SN2 substitution reactions in order to make alcohols. We saw that plenty last term. Alternatively, we could have a reaction that's a little bit different. But this time I'm going to use water. And we can also use this to form an alcohol. What are some key things to look for with this reaction? We've got a weak nucleophile, we've got a fairly hindered backside, so what sort of mechanism will this be? Yeah, SN1. So we could say weak NU. We can say that this can form a relatively stable carbocation. And we've got a good leaving group. So make sure that you are comfortable with SN1 and SN2 chemistry. It's not going away for the rest of the year. In particular, pay attention to stereochemistry when you're doing these reactions. Quite often when we do synthesis problems, people neglect stereochemistry. It's kind of reached the recesses of their brain at this point in the term. All right, we just covered a few other ways to make alcohols, so let's quickly address those. And we covered addition reactions in Chapter 9. So I'm going to ask you guys to help me fill in the reagent boxes. All right, how would we get an alcohol to add on to that center carbon? Concentrated acid, exactly. So we could say acid, and we actually want it dilute. Why do we want it dilute? It's mainly has to do with Le Chatelier's principle. Remember, we could do the reverse reaction going from the alcohol back to the alkene with strong concentrated acid and heat. So in this case, we normally want dilute acid. What's another method for adding on that alcohol onto a middle, or the more substituted carbon? Yeah, oxymercuration, demercuration. Why would we use that? Yeah, prevent rearrangements. So we'll treat this with mercuric acetate and water, followed by a reduction with sodium borohydride, and that will give you your alcohol, specifically if you're concerned about rearrangements. All right, what about if we want the alcohol coming off the less substituted side? Yeah, hydroboration oxidation. So we need BH3.THF, that's our boron complex, followed by hydrogen peroxide and sodium hydroxide. So we already know a handful of ways to create alcohols. When we come back tomorrow, we'll cover a few more, and then we'll start getting into new chemistry for making alcohols. All right, remember to work on the sapling tonight. Don't put it off tomorrow just because I gave you an extra day. Yep.